My name is Dr. David Bouras. I am a professor of economics at Lincoln University. My presentation for you today focuses on efficiency analysis with special attention to transportation. Introduction. Efficiency analysis is a powerful managerial tool that can be used to assess the performance of firms, industries, and organizations. Because of its positive features and advantages, efficiency analysis has been widely used. Some of its applications include logistics systems, transportation systems, supply chains, oil refineries, farm management, and so on and so forth. The objectives of my presentations are as follows: to provide an overview about technical efficiency, to survey various techniques of measuring technical efficiency, to analyze application of technical efficiency analysis in different transportation systems, and finally, to examine factors affecting or influencing technical efficiency in transportation systems. So what is technical efficiency? Technical efficiency was first introduced by Farrell in 1957, and according to Colley, 1999, technical efficiency can be defined as the maximum of output that can be produced from a given set of inputs and using the same technology. Inputs can include like energy, like capital or labor, okay? And analytically, technical efficiency is the ratio of the actual level of output to the potential level or maximum level of output. So let me use the following graph to make it clearer to you, okay? So in this graph, we assume that the firms use one single input, like for example, fuel or capital or labor, and produce one single output. For example, passengers, okay? And in this graph, there are two firms. We have firm A and then firm B. And then you have this curve is called the production frontier. And this curve shows the maximum level of output that can be produced from a given set of input, okay? So as you can see, firm B operates on the production frontier. So it's at its maximum. So if you were to compute its technical efficiency, which is the actual output divided by the maximum. As you can see, the maximum is equal to the actual output. That's why firm B is efficient, and its technical efficiency score is 100%. And for your information, technical efficiency scores ranges from between 0 and 100%. The closer the technical efficiency score to 0, the less efficient the firm. On the other hand, the closer the technical efficiency score to 100%, the more efficient the firm, okay? Now let's look at firm A. Firm A, its level of output is QA. And as you can see, it's below the production frontier. And that's why its technical efficiency score is less than 100. So it's not efficient, okay? Now, as for technical efficiency measurements, there are two main methods, okay? The first one is called the parametric method or the stochastic frontier. And the second one is a non-parametric method, and it's called data envelopment analysis. Now let's look at the stochastic frontier or the parametric methods. And let's consider an industry, for example, airline industry, consisting of n firms and producing an output Y according to the following technology. Okay, so the company uses energy E, capital K, and labor L. Okay, and E is the error term. So the stochastic frontier methodology consists of decomposing the error term into two components. You have V and then you have U. V is called the isochromatic term, and it captures all the factors beyond the control of the manager. And then you have the technical efficiency terms, and it captures all the factors within the control of the manager. So based on the definition of technical efficiency, we have to divide the actual output, Y actual, divided by Y max, or the potential, which is the exponential of this inefficiency term. Now, to compute the potential or the maximum output, we use the following function. So this requires the use of econometrics, okay? The second technique is called data envelopment analysis, which is a non-parametric method because it doesn't require the specification of a functional form, okay? And it has three assumptions. The first assumption consists of assuming a transportation system consisting of n firms. It can be 2, 3, 4, and so on, okay? And each firm uses m inputs to produce s outputs. And there are two major types of DIA models. We have input-oriented DIA and output-oriented DIA model. I'll explain to you the difference between input-oriented and output-oriented DIA later on, okay? And then it assumes two different technologies. The first one is called constant return to scale, and this one assumes that firms are operating at an optimal scale. Optimal scale means marginal cost or additional cost is equal to the additional benefit or marginal benefit, okay? And the second technology is called variable return to scale, and this one assumes that firms are not operating at the optimal scale due to, for example, imperfect competition or government regulations, okay? So let's start with the output-oriented DIA. Our output-oriented DIA means that the DIA maximizes output for a given level of input. Put differently, it shows how much a firm can increase its output for a given level of input, okay? So let's look at the model now. It's a linear programming model, which is beyond it's beyond the. So we have constant return to scale, which maximizes PK. The inverse of PK is called the technical efficiency score of the case firm. And then you have variable return to scale. So it consists of an objective function, maximize, and then two sets of constraints. The first constraint has to do with the output, and the second one with input. And then the third one ensures that non-negativity constraints. And lambda are called weights, okay? And then we have variable return to scale, same, maximize, the same constraint, only the last one. It assumes that the weights add up or sum up to 1, okay? Then we have the second one is called input-oriented DIA. Input, it means that that firm DIA minimizes input for a given level of output. Stated another way, it indicates how much a firm can reduce its level of input for a given level of output, okay? And similarly, there are two options. We have constant return to scale and then variable return to scale. The difference was the last constraint. Here, all the weights should take on non-negative values, okay, or positive values. And then for the variable return to scale, the weight should sum up to 1, okay? And then thetas are technical efficiency. And of course, to solve this kind of problems, you need to use software programs. You can use, for example, Lingo, Lindo, or GAMES, General Algebraic Mathematical Modeling System, okay? Or eventually, you can even Excel. If you have a small model, you can use you can use Excel to solve this kind of linear programming model, okay? Now, let's go through a simple numerical example, okay? for simplicity and purposes, we are assuming that the industry consists of three companies, A, B, and C. And the firm produces one output, for example, Tolmite shipping company, using a single input, for example, capital, okay? So let's compute the efficiency score for each firm, assuming constant return to scale technology and using the input-oriented DA model, okay? So try to remember these numbers now. So the first step you should do is to compute productivity indices. It's easy. All you have to do is to divide output by input. Let's look at firm A. Firm A uses three units of capital and produce 4 units of output. Okay, so if you divide 4 by 3, you get 1.33. Okay. Similarly, for firm B, its productivity index is equal to 1. All you have to do divide by output by input, 5 divided by 5, 1, right? Then finally, for firm C, the productivity index, you divide 3 by 4 and you obtain 0.75. So that was step 1. So step 1, you have to compute the productivity index for each firm. Okay. Step 2, select the firm with the highest productivity index and use it as a benchmark for computing efficiency score. If you look carefully now, firm A has the highest productivity index, 1.33, B1, and C0.75. So we are going to use this as our benchmark. So now, to compute efficiency score, all you have to do is to divide PI, the product index for firm I, by the benchmark. So for firm A, it's going to be 100 because 1.33 divided by 1.33 is equal to 100. So for firm B, you divide 1 by 1.33 and you get 75%. And for firm C, you divide 0.75 by 1.33 and you get 56%. And then you can compute waste. Waste is 100 minus efficiency score for firm A. So for firm A is equal to 0, okay? Because 100 minus 100 is 100 minus 100 is equal to 0%. Then for firm B, it's going to be 100 minus 75. It's going to be 25%. And finally, for firm C, it's going to be 100 minus 56%, which is 44%. So waste. So for example, for company B, the waste is 25%. 25% tells you that firm B can reduce its input by 25% and still be able to produce the same level of output. Okay? And then for company C, 44% tells you that company C can reduce its input by 44%, but at the same time produce the same level of output. Okay. So let's look at the graphical illustration. Here are the companies. You have A is on the efficiency frontier. That's why it's 100%. Company C, it's below the efficiency score. That's why it's less than 100. And same for B. B is below the efficiency frontier. That's why it's not efficient. Okay. Now let's go through some application of technical efficiency in transportation system. Let's start with so as you can see, technical efficiency analysis or the estimation of technical efficiency requires the specification of output and input. Now let's go through some examples. For example, in the railway industry, the output used in the literature are freight, ton kilometer, and passengers per kilometer. And 3 inputs have been used. You have length of line, number of locomotives and cars, number of employees, and finally, energy. Let's look at the airline industry. 3 outputs were used. You have revenue passenger miles, ton miles, and number of passengers. And 3 inputs have been used. You have number of planes, number of employees, and gallon of fuel used. Okay. So let's look at container ports. One output use container through outputs. And then we have like 6 inputs: terminal area, K length, draft, K equine, year equipment, and finally labor. So it's really easy. The efficiency analysis is easy. All you have to do is to specify inputs and outputs. If you have more than one input and one than output, then you have to use linear programming model and use Excel or other software programs such as games. You can use games. Then tracking industry, the output used was the revenue in dollars, of course. Then inputs are number of trucks, labor, fuel, maintenance expenditure on highways, miles of interstate, miles of non-interstate roadways. Okay. Now finally, let's look at the factor affecting technical efficiency. We have information technology, of course, and then company size. Why company size? Because the bigger the company, the more it leads to economies of scale. Remember, guys, the more you produce, the less the average cost it gets. Okay. Then merger and acquisitions. Why merger and acquisitions? Because usually mergers and acquisitions leads to economies of scope or scale. Okay, and economies of scale and scope leads to cost efficiency. Then you have ownership, public and private. Usually private is more efficient, usually. Then population density, network structure, technical progress, of course, human capital, educated people, of course, and investment. The more you invest on technology, the less the cost it gets, okay? So now let's look at some empirical examples. The first one has to do with US airline companies. Company efficiency score range between 82.6% and 100%, according to the study by Atul Rai in 2013. US airports, the average efficiency scores is between 73.6% and 83.6%, according to a study by Joseph Sarkis in 2000. And finally, in the US trucking industry, the average efficiency score is between 91.9% and 94.7%, according to a study by Weber et in 2004. And of course, as you can see, there is room for improvements. For example, in trucking industry, the waste is almost 5%. Okay. Conclusion. The main conclusion from efficiency analysis is that efficiency analysis has been widely used, as if you remember from our first slide, from supply chain, transportation system, farm management. And then there are two major methods, one called parametric method or software stochastic frontier method, and then we have the non-parametric method or data involvement analysis. The estimation of technical efficiency requires the specification of inputs and outputs. Usually inputs we use capital, energy, and labor. Output we use revenue, usually revenue in dollars, okay? And finally, technical efficiency is affected by several factors, especially the size of companies and ownership. And now, if you have any question, I would be happy to answer. Okay? Thank you.